Okay, now let's try to understand the difference between electrons, charge, and current. Okay, they are all interrelated. Now let's take a look at what is the difference. Okay, now let's take a look at electrons first. We know that electrons are part of the atom. Okay, now what atom am I talking about? I'm talking about the copper wire atoms now. These are the copper wires. The copper wires are the ones that provide the electrons or the delivery people to deliver the energy. Okay, now these electrons are free moving. Okay, and these valence electrons are part of the atom. Okay, they're mobile and they can move throughout the entire closed circuit when there is the presence of an electrical source. Okay, now if there is no presence of electrical source, the electrons are just moving around its own atom. Okay, so these are electrons. Now, and we know that there are millions of electrons, and so it is not very feasible to study each electron on its own. And therefore, we look at charge. When we talk about charge, we are referring to a basket of electrons. Okay, because it is easier for you to quantify a basket of electrons rather than individual electrons on its own. Now, how many electrons are in each basket? We have talked about this before. Each 1 coulomb, okay, a charge of 1 coulomb is equivalent to 6.24 times 10 to the power of 8 electrons. Okay, so when we say that there is 1 coulomb of charge, so 1 coulomb of charge is the same as telling others that this basket contains this amount of electrons. Okay, so electrons are the very small particles that is circulating within the atom itself. Charge is just taking 6.24 times 10 to the power of 8 electrons and putting them into a basket. Each basket is equivalent to 1. Okay, now then what is current? Okay, now current refers to how fast or slow this basket moves. Okay, so are these charges moving quickly or are they moving slowly? That is what we call current. So when we talk about having a large current, what you're trying to say is that the charges are moving quickly through the wire, through the circuit. So large current means that the charges move quickly throughout the circuit. If you're talking about a small current, when we say that the current is small, it means that the charges move slowly or move slower. So whenever we have to talk about how fast or slow something moves, it is always with reference to time. Okay, so when we talk about current, there is a formula that you can see below. Current is equals to charge divided by time. Okay, so just to recall, number one, electrons are part of the atom of the wire. Okay, and the electrons are mobile and can freely move throughout the circuit when there is an electrical source. Okay, if there are no electrical source, the electrons are just happily circulating within the atom itself. Okay, but when there is an electromotive force or if there is an electrical source, the electrons will move together in one direction. Now, electrons on its own is not very significant. So if you put many electrons together, how many? 6.24 times 10 to the power of 8 electrons together into one single basket, you quantify that basket as 1 coulomb. Okay, and that is charge with a symbol Q, all right? Then you move on to current. Current represents how fast or slow this basket is moving throughout the whole circuit. If the basket moves quickly, we say that the current is large. The larger the current, more energy is being able to be transferred quickly. Remember, we talk about how the charges are actually like the delivery people. If the delivery person can move faster, things can be delivered quickly. So likewise, in a circuit, if the current is large, means the charges move quickly, means the energy can be transferred quickly from the source to the various electrical components. Okay? And if the current is small, it just tells you that 1 coulomb of charge moves slowly. Okay? So the slower they move, the slower the energy is being transferred. So there is a formula when it comes to calculating current. So current is therefore equals to the amount of charge divided by the total time. That will tell you how much or how large or small the current is. Okay, so now let's take a look at a simulation, a battery. All right, okay, it's always a good practice to have a switch so that you can control when to close or open the circuit. Right now, it is a open circuit. All right, even if there's an electromotive force, nothing is happening. Okay, now let's close the switch and see what happens. So the moment you close the switch, the electromotive force within the battery will cause the electrons to start moving in a single direction. Remember, the electrons come from the copper wire itself. Okay, so in the presence of the battery, the electrons will move together in the same direction, just like your water pump. Remember, we think of a circuit like a water pump. When the water pump is switched on, the water will flow in the same direction. So likewise. Now, let's build another circuit to show the difference in the current. Okay, but we add a resistor. So let's take a look. Okay, so when you close this, now can you see that the current on the new circuit on the right-hand side is slower? Okay, the current on the right-hand side is slower because of the presence of an obstruction or the resistor. On the left-hand side, you realize that the current is flowing faster. Okay, so we say that the circuit on the left has a larger current than the circuit on the right. Okay, now since we are here, let's talk about how do we measure current. Now you have two instruments that you need to be very familiar with, the voltmeter and the ammeter. Okay, now as the word suggests, ammeter is measuring the current. Okay, it is related to the word ampere, and ampere is the SI unit for current. Now you want to measure the current, you must make sure that the ammeter is in the path of the current. Otherwise, you cannot measure the size of the current. So you simply place it here, you will be able to tell the current flowing through that particular piece of wire. Okay, so the ammeter must be in the path of the current. So this circuit on the right shows you 0.45. How about the circuit on the left? 0.90. As expected, the size of current is larger. So again, current just means how fast or slow the charges are moving. Okay, now just to bring home another point about electric charge. Okay, so remember, charges are your delivery person. Okay, they are delivering energy from the source to the various parts of the electrical circuit. Example, your aircon, your light bulb, etc. So therefore, the role of electric charges is really to carry electrical energy from the source to other parts of the circuit. So you realize that the green color packets represents the energy from the battery. All right. So the green particles represents the electrical energy from the battery. So the red color particles are the charges. The charges are merely delivery people. They will not disappear. They are simply moving around the circuit, delivering energy. They will always start from the cell and they will always end with the cell. Now, what is the difference is the energy. So you realize that once the energy is being delivered to the electrical components, in this case, all the energy is given to the light bulb, then there is nothing left when they come back home. Okay, so every single charge carries enough energy to be supplied to the light bulb to be converted to heat and light. Okay, we'll talk a little bit more about the 6 volt when we come to EMF and when we come to potential difference. Okay, but the main important concept you need to know is charges are the delivery people. They are the delivery guys within the circuit, closed circuit, within the closed circuit. And what they carry with them is simply the electrical energy. So electricity is a phenomenon, right? Where energy is being transferred from one point to another. And this explains it. You need to be aware that there are 2 directions to take note of. Okay, whenever we talk about current for calculation, whenever we talk about what I symbolizes, whenever we talk about SI unit as ampere, as well as any formulas, we are referring to the conventional current. Now, conventional current was discovered, or rather it was scientists had always thought that the positive charge or the protons were the one that were mobile. Okay, this was way before the discovery of electrons. Okay, so conventional current takes the point of view that positive charges comes out of the positive terminal of the cell, okay, and it is represented by I. Okay, so in all of our calculations, in all our understanding of current electricity and the solving of circuits, we will always be assuming the conventional current direction because of the way it was discovered first. Okay, but later on, much later, they discovered electrons. Okay, but the scientific world has come to an agreement that they will not forego the conventional current direction. They will continue to use it, but they know that at the back of their mind, it is really the electrons that are the ones that are mobile. Okay? So when we talk about current, we are always talking about conventional current. The symbol is I, the SI units is ampere. Formulas, etc. will all assume a conventional current stance. So the conventional current, symbolized by I, comes out of the positive terminal, flows through the closed circuit, and goes back. Now, it was only much later they discovered electron flow. Okay, so electron flow was discovered much later when they realized that it was really the electrons that were moving throughout the wires due to it being on the outer shell of the atom. Electron flow is actually in the opposite direction to the conventional current. Okay, so if they were to ask you to label the direction, the electron flow comes out from the negative terminal of the cell. Now, how would a typical O-level question look like? A typical O-level question will look something like that, and they will give you a circuit diagram, either in MCQ, usually in MCQ format, and they ask you to label or identify the correct directions for conventional current and electron flow. So first and foremost, if you were to identify the conventional current, we assume that it is the protons that are carrying the energy and are mobile. So therefore, conventional current comes out of the positive terminal of the cell, symbolized by I, and this is the direction of the current. If they were to ask you to identify the direction of the electron flow, then you must know that the electron flow is opposite to that of the conventional current. So the electron flow will be in the opposite direction and it comes out from the negative terminal. So electron flow is seldom used in calculation, illustration. Actually, we never use electron flow, but you need to know at the back of your mind, it is the electrons that are really coming out, or rather it is the electrons that are flowing through the wire, not the protons. So just to recap, for our study of current electricity, even as you go on to tertiary or university, we will always adopt of conventional current in solving problems.